Okay. Thank you, Mark. I guess at any point, let me know if something is not readable. I've zoomed in a little bit on my side so that things look like they are uh, like friendly for elderly readers. So I think that that should be good for you all, hopefully. Also, I will just
Could you
a note
zoom in a little
before
more?
I
Is it possible?
yes, I will say the graphs are a bit smaller than the actual text. So. Um, so there is that. Do you still, seeing that the text
If
will be
you,
this
if
size,
you
should
could
I
do
still
one
zoom in
more,
more?
if you could do
Zoom in
one
one
more
more.
level, that'd be like,
Okay. Okay. Um, all right. Okay, so oh yeah. Well, I'll just say I think that this presentation might be short. I have thought that before. I'm not always well calibrated. But what I want to say is that because I think this might be a short presentation, definitely feel free to interrupt at any time. Um, although with the proviso or the proviso that you might be recorded while making an interjection. As long as you're fine with that, I encourage you to pipe up at any point and ask specifically like a low level question like how exactly was this implemented or I didn't quite get that. Can you repeat that? Those types of questions. Okay. So with that, I've just placed these graphs here as sort of a reference point. Like these are graphs that you have probably seen. They do not come from this paper. At the very end of the presentation, I'll get how what happened in this paper relates to these graphs. But these are probably the most widely distributed, updated, discoursed about graphs in all of AI right now. Um, so the one thing I will point out in these graphs before we like go through a long journey to get back to them is just that the y-axis, so vertically running here, is time. So the first one, which is on this log scale, uh, don't worry about that, but goes, you see here, again, it's a little bit small, but goes from 4 seconds, 36 through 6 minutes. So it goes from seconds to minutes and then tops out at 10 hours. And so that is human time. So you'll see that the label for this axis is task duration for humans. So that's what this presentation is going to be about. Like, where do these numbers come from on the y-axis? Okay, so introduction. Um, this paper, so HCAST is its acronym. It's Human Calibrated Autonomy Software Tasks. I will say that is not the most grammatically exciting way to combine 5 words, but it is what it is. Um, so that's what it stands for. And I would say that this is about doing measuring autonomous capabilities. And there's a little dash of economic relevance, although that's not talked about as much. Maybe it's less important from an AI safety perspective, although maybe it is. We could talk about that. But in any case, um, so with these tasks are created so that they are like they're benchmarks, right? That's something we talk about a lot in these evals meetings. Most of the benchmarks we talked about are multiple choice questions, often get abbreviated to MCQ benchmarks. And one issue with them is that they don't have a lot of real world usefulness. There's not an obvious mapping between like 95% on MMLU and anything in the real world. So what the authors did here, or what Meter did, was to anchor this to human time estimates. And then the idea is that that will give an intuitive metric for understanding the real world impact of autonomous systems across economically valuable domains. And as far as what those domains are, I'll get to those in, I think, the next section. Um, but yes, it is not a random sampling of economically valuable domains. Maybe at the end we can talk about that as well, the extent to which that's relevant or not. Autonomy is a big word here, so I thought that's worth spending some amount of time on. So very early in the paper, like they hone in on this, and they home in on this, they say, in order to measure the autonomous capabilities of frontier AI agents. So like that is really what this is about. And so perhaps like these bullets could have been better ordered. Maybe the next one is like the way that they've done this, the way they've thought about this is now jumping down to the third bullet. They say like that each task here is intended to represent a single end-to-end activity a human might undertake. So that plays into this idea of autonomy, right? If a model can do this from end to end, then it can autonomously do it. Um, and these tasks are, I'm jumping down to the fourth bullet now. So they're more open-ended and or require exploration. So that's quite a bit different than like the old knowledge-based benchmarks where it's just what is the correct answer, A through D, select it. Um, so they require like interacting with an environment as an agent will do. And to further situate this, so that this is a post you might see. So this is Chris Painter, which I'll just take an aside to say that if you use X or LinkedIn, um, Chris Painter is probably one of the best people to follow in this area. So I would really recommend that. But this is like how updates to this graph get portrayed. So he's writing here, and this is actually from 5 days ago. This is the most recent update, I believe, to the meter graph. That so a year from now, or sorry, 2 years from now, software projects that would have taken a pre-AI human software engineer 2 working months to build will have a 50% chance of being completed by an AI with a single prompt. So there you see in that last part, completed with a single prompt, that's the idea of autonomy, right? That you give it a prompt and it goes off and does this without further human interaction. And you also see like this time measurement, right? So that's the idea is that like that's how we're measuring how difficult the task is how long it would have taken a pre-AI human expert, in this case it's a software engineer, to do the task. Okay, um, I think I'm going to skip economic relevance further, but again, we can come back to this. So yeah, so let's look at like what the tasks actually are. So there are 189 tasks here. They're all this agentic nature. Um, they come in 78 families. So there's some taxonomy going on here, where a family is just related tasks. So maybe like a bundle, and sometimes bundles are singletons. They have just one member, and they can have up to 5 members. Um, they do have summaries of each family. I believe it's each family, or perhaps it's one level above abstraction in the summary, sorry, in the appendix. That I did peruse that, or at least I did skim it, and it was interesting to look at those. So I would point you to that, but obviously this would not be a very productive presentation if I just ran through all of the 78 families. So I'll just say that um, like so if you want to do the first cut of like what these tasks are, it's what the domain the task comes from is. And there are 4 broad domains. There's MLE, so machine learning engineering, software engineering, cybersecurity tasks, and then general reasoning tasks. Those are the 4 big buckets. And I've given one example in like sort of written out narratively what it is, and I've given some other examples. So just very briefly, something that a machine learning engineer might do, and might be automated in the future, is to train a sentiment classification probe on GPT-2. Since it's a sentiment classifier, it's saying positive or negative, and it's basically like doing this from scratch. And there are other MLE tasks. They have this pretty cool one. This is one I would highlight to you to check out later if you get a chance or if you're curious. There's a sparse adversarial perturbation task where you're trying to create adversarial examples to trick an image classifier. There's trying to fine-tune a chatbot to give answers in acronyms. So some pretty cool little toy tests. but that are relevant to like what actually happens in the world. Um, and for almost all of these, there's like also a pre-existing paper. That's what these are, by the way. So there's an MLE bench. When I get to software engineering, there's a SWE bench. It's probably like the most famous benchmark actually. And then there's some like cyber benches as well. But anyway, um, I'm not going to dwell at quite as long on the rest of these categories. But so for the software engineers, like this is the one that I've given the narrative text for is like a pretty complicated one. I don't remember what its estimate in hours was, but it very high or relatively high. So this is like pretty complicated. Also, making a web server is quite a bit more simple. Um, Another one they had was there used to be this bug in PyTorch, which is a library that uses Python code to do like low-level, well, basically to train um, LLMs and other deep learning models. Anyway, there was this bug at one point that caused things to be very slow, and one task was to find the bug and fix it. So that's some software engineering stuff. There's some cybersecurity stuff as well. For example, doing SQL injections, and also one fun one was to find vulnerabilities in Ethereum contracts. And then in general reasoning, for example, doing like statistical reasoning and thinking. So um, here there's inferring a function. Some other examples were doing like local research, being basically given a bunch of documents and asked questions about it. And then one is continuing a pattern. So getting um, basically like an IQ test for a computer, essentially. So those are what the task families looked like. And as far as how they were actually implemented, they got in, so they being both humans and models would get an instruction string. That is just a plain text representation of what you're to do. You get what's called a containerized environment. It's not important if you don't know what that is. Basically, just like a computer within a computer might be a relatively accurate and quick way to describe that, along with some setup code. So they would get both, again, humans and models would get like the packages they need, specific, also like resources. So in this example for sparse adversarial perturbations, you can see that the resources are a text file that for some reason has a Python logo next to it. But anyway, a text file that is just the requirements to be met and a data set with which to train your model. So you get those, and you get a scoring function that is deterministic. So yeah, it's completely automated, and it's either correct or not. So it's a 0, 1. And sometimes there were thresholds. So for some like optimization tasks, like a task is not optimized or not, but they would set a threshold, say like you have to have sped up the process by such and such percent, or else you have failed. So that's how continuous things were made into like a binary success failure uh, metric. And then one fun thing to note is you may have heard, I believe it was, I think this has happened multiple times, but sometimes in these agentic scenarios, one way that models will succeed is by just finding the code that grades them and saying like, oh, success. So by virtue of having done this containerized environment thing, they could not give the model root access, and they only give root access to the scoring function. So these actually run separately, and the scoring function runs at a lower level that cannot be messed with by the model. Um, okay, I'm going to ignore this thing down here, this bit of text. And so that's what the tasks look like in detail. And again, there are 189 of these at different levels of complexity. Again, feel free to interrupt at any time if you feel like you don't know exactly what's going on. Okay, this section I don't want to spend too much time on because it was so this article was published a year ago. Um, with like the initial models, and you'll notice that these models are not the ones that are currently, in use. In fact, I just saw the other day someone publish a medical advice study where it seemed like the main critique, or not the main critique, the main response of it was, you published this using like LLMs that people stopped using like 2 years ago. Um, and again, so that would be like not, so the particular models that were used and then the results that they generated are not what we should be taking away from this paper, but it might just be of somewhat historical interest to note this. So well, there's also like a more enduring methodological note, I guess. So the models that were used, there were like two classes of models. There were non-reasoning models, so non-natively reasoning models. Those were GPT-4o and Claude 3.5 Sonnet. And Meter placed these in a React scaffold. Um, it would be a little bit beyond the scope of this presentation to say what React is, but React is sort of an abbreviation of reasoning and acting. And the idea is just that you prompt a model. Like back in the day, chain of thought was done by you actually just go to a non-reasoning model and you say, like think step by step, right? React is kind of the same, where you're like, okay, generate some reasoning and then end with some action. And then you would like parse out the action, and like that's what would happen in like a terminal. So that's the way React used to, like agents used to work. So they did those for the non-reasoning models, and then they had reasoning models as well. At the time, it was O1 Preview and 3.7 Sonnet Extended Thinking. And they came up with a scaffold they called Triframe, which is a very interesting, just like if you want to know maybe like if any of you use Cloud Code, Cloud Code has a planning mode that it'll go into if you ask it to do anything kind of complicated. I don't know what's going on under the hood. I don't know if anyone outside of Anthropic knows exactly, but if you're curious about what kinds of things these people are thinking about, this is a pretty interesting example where this triframe, it's told to plan, and then it generates three next step. That's what the command here means. Three next step possibilities based on the plan. Then three command possibilities that are not based on the plan that sort of ignore it. Um, and then, so you have six possibilities there. And then it rates each of these six possibilities on a 2 to -2, or I guess I'll start at the bottom, -2 to 2 um, scale. And performs like the best one of those. So it generates six possible courses of action. And the reason they do based on plan and not based on plan is to generate like a more diverse set of possible actions. Then it again rates all six and picks the best one. And that's how it decides what to do at every step. Again, because like some of these tasks are at least, would take a human many hours. These are like multi-step tasks. So each step is like done like this. So I think that's an interesting scaffold. Um, yes. But one thing to know about this is that like now when you see results, you have to think, okay, this is not only like just abstractly how 5.2 now that we're in like I guess we're in Codex like 5.3. Like uh there's not like an inherent score for how 5.3 does on something. It's like how 5.3 does given a particular scaffold. And now it's a little bit more difficult now that these things do have scaffold. Like 5.3 is like a model and a scaffold already. So things have gotten a little more complicated since Claude Code and OpenAI's Codex came out. But now we have Matt who's going to say something interesting.
Well, yeah, so that's right. And I've also heard that these can make a material difference in the performance. I think there was like one well-known paper that used their own scaffolds instead of Claude codes, and then like the performance was much lower than Claude code could actually achieve with its own harness or something like that. But in one important way, it isn't important, I think, in that it's it doesn't matter quite like how much reasoning effort, right? The ultimate thing is whether or not it succeeds at the task or not. So if it has to do it with like 5 times as much token usage, In some sense, that doesn't matter because the relevant sense of time here is really just like relative to how often the human gets it correct or something like that. Isn't that right?
Um, well, we can open this up for discussion. I will say
Sure,
so
later.
at
That's not a
the yeah, I will just say I did have a note here specifically saying that at least when they did this a year ago, um, they said that they limit runs to 10 hours of human time, and for the what they call the modular scaffold or harness, which was used by GPT 4.0 and Claude 3.5, there was like a 2 million token limit. And then for the tri-frame agents, again, those are the reasoning models embedded in this scaffold they named tri-frame. They said you could have 8 million tokens. And yeah, we can talk about this more in the discussion, but the very quick explanation for like why you would want to limit these beyond just like, we're meter, we don't have infinite money, is that for the economic relevance part of this, right? Like if your task takes 10 hours to do, but let's say that it took a human like 5 hours to do, then like maybe you would want the human to do it again, depending on the cost of tokens. And that's like the second part is that maybe if this takes some exorbitant amount of tokens, then maybe it would be relevant. Like, I mean, it's indicative of something like from like a fundamental perspective, but it's also it does like cost money. Like that is how cost is measured, like cost per token. So anyway, so I think that there is actually a reason for thinking about clock time and token per, well, yeah, number of tokens taken up. But we can talk about that more in the discussion. Um, yes, the last note I had here was about the term that was used quite a bit back in the day with unhobbling. So the idea is that like chatbots, the way they were trained is kind of they were in like some hobbled state where they had probably a lot of like latent capabilities that were just like waiting on some like relatively quick post-training RL unhobbling, or like a scaffold or like tools. Um, so the idea here is just to note, this is a reference to like what I was saying earlier about um, these models, there's no like inherent score that they would get on this benchmark. It's like the model plus the degree to which it is unhobbled. And right, so they're saying here that they want to say that their results are actually like lower bounds in the sense that had they optimized prompting and scaffolding better, performance would have been better. So that's always something to keep in mind. Not only for, HCAST, this paper, but just anytime you see like this is how well a model did in any real world scenario. Yes. Okay. Um, so this is actually pretty important and somewhat unique to this paper. I think that it's at least been a very long time since we've talked about humans in in this evals group. Um, but this is like very important, great, because like the whole uh, I guess the French would say the raison d'être of this paper is to like figure out how long this would take in human time, and like so they had to time humans, right, to get that. And so, in case you're curious where these estimates come from, they had 140 people who they refer to as baseliners to get the human baselines. They made 563 attempts at these tasks. These were in general like people who were impressive on at least their CVs. They most of them, or perhaps all of them, either came from a top 100 global university or had more than 3 years experience. And they also mentioned in the paper that they were people who the meter people knew, a lot of them, so they would find them through their professional networks. And then if all that is like it seems insufficient, they had to pass a domain-specific qualification task test there. So that's like the people. And then as far as what it was like for them to do it, they were allowed internet, but no AI. And so the idea is like, I'm not going to scroll all the way back to it and introduce like, well, maybe I will just real quick. So, because I don't need to scroll, I hope much, you'll notice that when Chris Painter talks about this, he says, how long this would have taken a pre-AI human software engineer, right? And so what that is referencing is that people are not allowed AI, but allowed to use internet, so like they could access like Stack Overflow or something. And the idea was that when they were testing this, and they didn't allow internet, people would just like forget how to do a specific thing in like the whatever language they were programming in, and that just represented like and not allowing people to use internet was like uh, very dissimilar to what their actual workflows were like. So that's the level of like technology that was kind of like frozen here. That's like the snapshot of time we're getting is internet but no AI. And they also had to access their environment via SSH to give kind of what they call an interface parity between the models and the humans. Okay, so there's that. And then maybe this is just because I come from a world that is interested in economics and like incentives that I found this interesting, but I think it is pretty relevant. So these people had an hourly rate, but now if you think about just giving them an hourly rate, what does that incentivize them to do? To take as long as possible on these tasks, right? And so imagine that was all they did. And then like one obvious critique of this paper would be to say all of these estimates are overestimates, like your estimates of AI capabilities are overestimates because you essentially incentivize humans to take as long as possible. So you're saying that AI can do this 20-hour task, right? But that's obviously not a 20-hour task. That's a 10-hour task that some human took 20 hours to do because they wanted you to pay them twice as much, right? So that would be a pretty obvious critique. So what they did was, and I apologize for not explaining the notation here written, but I will do it verbally. So this hourly rate for an individual is just R. And so basically you can think of this little formula here that's in the second bullet point under incentive structure as they got this bonus whenever they completed a task. What that was their hourly rate divided by two, but it scales with their hourly rate times the average time it took that task. So if this was a really hard task, and they did it, and then the person did it successfully, right? They could be paid, they would get a bonus on top of this. And they would get more for completing, they would get more money for completing more difficult tasks. So a task that took on average twice as long would have twice as much of a bonus. And it's also not a lot, especially as like, well, anyway, but okay, this was like a success incentive, right? Because one thing I should have mentioned with the hourly rate is that you could charge this even if you failed to complete the task. So this very last part here, the third outermost bullet, uh, says that if a person completes this faster than any other baseliner, they get another bonus that again is their hourly rate times the average length of the task. So that it took the task. Anyway, that it took people to do the task. So that was the speed incentive. So that is how they incentivize both success and speed. Anyway, so I found that interesting, and there were two things that were important to incentivize. I'm sure a behavioral economist, I think probably could have done a better job, um, but anyway, but definitely like good thinking there. Maybe things we can talk about in the discussion. The results, I'm mostly not going to talk about just because, again, I think the results of what was going on in 2025, a year ago, pre-Claude Code, pre-OpenAI's Codex are like not very important. Um, but I will say that one thing they found and one thing that continues to be true is that, and this is very intuitive as well, is that like number of actions is a very important variable. So here what you're seeing is just like a description, basically a visual description of the mean number of actions that these tasks took. And so you see here, like at least a year ago, when these were being completed, like models were taking, like you see this big hump here. So it's a pretty skewed distribution, but you see like a lot of the mass is like tasks that take fewer than 10 actions. But you do see this long tail of tasks that take up to almost 30 actions. Although keep in mind that the y-axis is pretty small. So like over far to the right, you see that there were like two tasks that fall into this bin that's centered on 25 actions. I have not seen an updated version of this. It's possible that models could be, I mean, various things could have happened as like more tasks are completed by models, like the right tail could be going further out. I assume that's tr becoming true, but also for any given task, it's probably being pushed to the left, in the sense of like towards lower numbers because models are getting better at doing things in one shot. Um, so those are two like countervailing things. And it's also probably worth talking about particular failure modes. So again, these were models that were like this was like the infancy of tool use in computer use. So I think it would be interesting to know to what extent these are like persistent failure modes. But sometimes models would abandon tasks. So they would just, there's something that they had tried that they had gotten feedback that was incorrect, and they would just submit that as their final answer anyway. So that's what that would look like. Sometimes they would persist in strategies that they kind of could very easily infer were not going to work. Um, there's this one quote that I believe is like a misattribution to Einstein that insanity is repeating things that you have seen fail before, or something like this, or maybe it's inverted that like success is not doing that. But anyway, these models were not good at this. They would try things that had failed and try get them again. They were not very good at resource management occasionally, so especially for more difficult tasks. They were like alerted that they were reaching the end of their token budget, and they would just do very strange things, like immediately react. And again, this makes sense because models at the time, like at no point in their training, like did they have to sort of obey and react to a token budget. So that's again why like some of these would be interesting to come back to. Um, and also they were moving on to the last bullet point. They're not very good at navigating what the authors call low feedback environments. So they weren't very good at doing like open-ended exploration and like making the most sense, getting the most information out of ambiguous environments. So those are some failure modes. And just really quickly, some limitations on these tasks. So on interpreting these as like autonomous tasks. So I guess the way you can think about this is like how the distribution of these tasks is not the same as like the ones that you and I would do in our jobs, slash the ones that are relevant to like, I don't know, like ML researcher abilities. So most of our tasks are they have some sort of context, there's some like institutional context, or there's some relevant personal background. All of these tasks were created to be contextless, and it's just sort of a necessity, at least, or maybe not a necessity, but that made things a lot easier. Um, while they weren't, so moving on to the second bullet point, while they weren't multiple choice questions, they did have to have like easy evaluations, so like algorithmic scoring. So there was that. Um, they were all like specifically not only contextless, but like solitary software tasks. So it had to be like a discrete part of a workflow that all happens in software and like doesn't require interacting with a human. Um, and then the very last limitation I'll point out is this is more of like a human aspect, is that 50 of the tasks of the 189 just ended up without a baseline um, because they didn't get a human to do it. And even among those where humans did give baselines, like there were a lot of attempts that did not result in success. And I'll leave it to the, if you want to read the paper, there's some like explanation of how exactly that would happen. And then lastly, just to tie this back in, I said I would like explain how what goes on in this paper is sort of like a necessary but not sufficient condition for the famous meter graph. So that graph comes from a paper that I think we actually might talk about in a future meeting. So that's the time horizon paper. So in that paper, they talk about a suite of data sets that were designed to capture all the tools necessary for reasoning sorry, for research and software engineering. So notice that this is like a different purpose. It's like a different subset. And there, what are included are RE bench, so research engineering bench, a subset of these tasks. So again, we've been talking about HCAST, and then a new set of short tasks, SWAA, which stands for software atomic actions. Yeah. So yeah, so the task set, the group of tasks in the meter graph, the famous meter graph, are not just HCAST, but are rebench these tasks, and they're not also all of HCAST. Um, so yeah, so that's that. I've included some links. I will somehow find a way to share this presentation, um, but some useful supplements. Um, but I will end the presentation there and open the floor for anyone who wants to say anything about this paper.